Hi, Assalamualaikum. Good morning, everyone. This is CHM477, Inorganic Chemistry, lecture number 9. I'm going to start on a new topic today, which is transition metals, which will lead us to coordination chemistry. Transition metals are metals that play a huge role in our daily life. Of course, we have iron, copper, titanium, silver, gold, platinum, and so on and so forth. Some are being used as our daily items in the house or at work. Some are being used for catalyst. Some are being used for medication, and so on and so forth. We also have chromium. Chromium is very well known as a supplement for people who are diabetic, and nickel, iron, all those are very important elements in our biological system. Now, what are transition elements? Now, transition metals are defined as a metal which has at least one ion with incompletely filled d or f orbitals. Incompletely filled d or f orbitals. So first of all, you need to know what are d orbitals and what are f orbitals. Previously, we have encountered d orbitals. We have 1s, 2s, 2p, 3s, 3p, 3d. These are the elements which has d orbitals containing valence electrons. Now, if you look at the periodic table, you will see that those are the elements that are shaded in blue here, from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc is not included as transition metals because it doesn't have incompletely filled d or f orbitals. The f orbitals is way down here after the end of this periodic table. You have the lanthanides. Then those are also transition metals. But for the purpose of 477, we are only going to deal with the transition metals that have d orbitals, electrons in the d orbitals. Okay, so there are more than 50 transition elements. Each one element or each one transition metals has its own interesting and very varying characteristics. Now, the general properties of transition metals are very much like any metals that you encounter in the main group or in the representative elements. The most outstanding trend is the noticeable change in the chemical and physical properties of the elements in the same period, that means in the same row, as the number of valence electrons changes. Yeah, as the number of valence electrons changes, that means it moves from from the left of the periodic table to the right of the periodic table. You have an increasing number of atomic number, an increasing value of atomic number, meaning that there is an increasing number of electrons as you move along from the left to the right of the periodic table, and that is the same in the transition elements. There is also a very noticeable change in the chemical and physical properties of metals as you move from left to the right. Yeah. For transition elements, the similarities in the chemical properties are observed in the same period as well as in the same group. Same group means in the same column. Yeah, the same column. This occurs because the last electrons added to a transition element are inner electrons, which are electrons in the d orbitals for elements in the d block, and f electrons for elements in the actinides and the lanthanides block. The inner d and f electrons do not take part readily in a chemical bonding compared to the electrons of the s and p orbitals, but they do uh, um, have some activity going on. Now, if we move from left to right of the periodic table, the atomic number increases. Yeah, this is very, very common. This is what the characteristic of periodic table is. Electrons are added in valence shell, and the nuclear charge increases with increasing number of protons. Taking the third period, that means the third shell, you have the 3s, 3p, and the 3d, which is from sodium to argon. So let's have a look at sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Taking this third period, you see this is the 3s, this is the 3p, but here is your 3d. 3d is located on the fourth period because 3d comes after 4s. If you remember the Aufbau principle, yeah? So you have 3s, 3p, 4s, then 3d, yeah? Uh-huh. The addition of valence electrons causes a noticeable decrease in the atomic radii. That means the atoms become smaller because valence electrons only weakly shield each other from the nuclear charge pull. As for transition elements, for example, from titanium to copper, the decrease is less noticeable because electrons are added into inner orbitals, which are the 3d orbitals. Consequently, the electronegativity and the first ionization energy values are also slowly increasing as shown in this graph below. There is a construction work going on, so let me just pause this for a while. So looking at this table of ionization energy as we move from scandium, titanium, vanadium all the way to copper, you are going to see that the first ionization energy is not changing very much as we move along because the electrons are added in the inner orbital, not in the outer orbital. So the changes are not very, very um, uh, apparent. Second ionization energy, that means the energy needed to remove the second electron. There is a little bit of a slight change comparatively more noticeable than the first ionization energy, but removing the third one also gives us quite a distinct change of energy needed to remove the third electron. So those are the plots for the energy needed to remove electrons, first, second, and third. I'm not going to dwell too much on the properties of transition metals. I'm just going to go straight into the electron configuration of the first row of transition metals. Now, I think I'm going to have to move the periodic table here so you can be able to see it better. Now, calcium, here is your calcium. That is calcium. I hope you can see this. Oh, I'm going to have to do this. Yeah, that's your calcium. Calcium has electron configuration of argon, which is the inner argon, 4s2. This is 4s1 for potassium, and calcium is 4s2. Now, the outer electron configuration of scandium, then, after you finish with the 4s, the 3d come next. So the scandium here will have one electron more than calcium. Yeah, scandium here has one more electron than calcium, so it is 4s2 3d1. Titanium is 4s2 3d2, vanadium 3d3, chromium 3d4, and so on and so forth. Yeah. So as you move along, this is uh, argon 4s1, argon 4s2, argon 4s1 3d1, argon 4s1 3d2, 3d3, 3d4, and 3d5. Okay. So that is how electrons are being filled. And with the filling of the electrons, you're going to move from one element to another in the periodic table. Now, you would say this is 4s2, 3d4. Yeah, chromium is 4s2, 3d4. And this would be 3d5, 3d6, 3d7, 3d8, 3d9, and 3d10. Well, that is well and good, but there are some exceptions. There is always an exception to a rule. Yeah, there are two exceptions, which are chromium and copper. Chromium and copper has outer electron configurations that are 4s1 3d5, that is for chromium, and 4s1 3d10. Now, you might be wondering why here this is your chromium. This is chromium here. It should be 4s2, 3d1, 2, 3, and 4. 4s2, 3d4. Yeah, for chromium, that is what we estimated, or that's what we follow the flow. It will be 4s2, 3d4. However, that is not happening. What happens in real life is 4s1 and 3d5. Oops, yeah, 3d5. So chromium, set here, chromium. Four s two, 4s2, 3d4. Yep, that's what expected. But however, that is not happening. What we observe is it is 4s1, 3d5. Yep. Four s1, 3d5. Why that is because there is an extra stability associated with half-filled 3D subshells. Now, if you can recall, elements have the utmost desire to be very stable. So by moving this paired electron from the 4s into this empty d orbital here, you get this arrangement. And this arrangement offers extra stability because it has half-filled 3D subshell. So that is why your chromium is 4s1 3d5 instead of 4s2 3d4. And there is also an extra stability associated with full d orbitals. That is why you have copper. Yeah, that's why you have copper instead of 4s2 3d9 for copper. Yep, this is d9, this is d10. Instead of 4s2 3d9, copper is 4s1 3d10. extra stability is associated with the completely filled 3D subshells. Yeah, completely filled 3D subshells and half-filled 3D subshells will give extra stability to copper and chromium. That is why it has a slightly irregular pattern of electron configuration. So if we go from scandium, now I would like you to, everybody, try and remember the arrangement or the order of metals that appear in the first, this is called the first series of transition metal. This is the first series transition metal. This is the second series transition. Okay, this is the first series transition metal. Yep, the 3D. The second series transition metal is the 4D. This is 4D elements. And this is the 5D elements. This is the third series transition metal. So I would like everybody, all of you, to try and make whatever you need to make, rhyme or song or pantun or whatever, so you can recall scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. It should be rolling off your tongue. Yeah, it should be like a nursery rhyme. You should have scandium, titanium, vanadium, chromium, manganese, iron, copper, nickel, cobalt, nickel, copper, and zinc. I have my own little rhyme that I'm not going to share with you because it is a bit silly, but you can make your own silly little rhyme so that you can memorize the order of appearance of these transition metals, at least in the first transition metal series in the 3D um, group. Yeah, these ones. So scandium, as I mentioned to you earlier, is argon 4s2 3d1. Titanium, argon 4s2 3d2. Vanadium 4s2 3d3. Chromium 4s1 3d5. Yeah. Chromium is 4s1 3d5. Why the irregularity? Because this arrangement is half filled d orbital gives extra stability. And then when you come to manganese, you start having 4s2 again, 4s2 3d5. Iron is 4s2 3d6. It's not ferrum. Okay, we are learning in English, so we don't say ferrum, we say iron. Cobalt 4s2 3d7. This nickel is 4s2 3d8. Copper is here 4s1 3d10 because of the extra stability of the full d orbitals. And then for zinc, it is 4s2 3d10. So that is how the d orbitals are being filled in as we move from scandium to zinc in the first series of the transition metals. So if you want to see how the orbitals are filled, do this. Yep. This is your scandium, 1 electron on the D, titanium 2 electrons, vanadium 3 electrons, chromium 5, and then manganese 5, but 2 here, and then iron 6, cobalt 7, nickel 8, copper 10, because 1 is missing from here, 1 has hopped, has jumped onto the G, and then zinc is 10. So if you look at the number of unpaired electrons, here you have 1 unpaired electrons, 2, 3, 4, 5 unpaired electrons. But when you come to iron, the d electrons start to pair up, because if you remember the Hund's rule, you have all the orbitals has to be filled in singly first. After all the orbitals are full with single occupation, then they start to pair up. So pairing up begins at iron. So you're going to have, instead of 5 unpaired electrons, you get 4 unpaired electrons. Cobalt 3 unpaired electrons, nickel 2, and there is no unpaired electrons for copper for the D, but there is 1 unpaired here, and zinc is 0. So this is the electron configurations and other properties of first row transition metals. You're going to see there is a trend to the radius, to the standard reduction potential. The trend is here. You can have a look at the values. So I'm going to go straight into the unique properties of transition metals. Now, transition metals are very, very special because they can have different oxidation states. If you look at your periodic table here, go back here, lithium will always be lithium 1. Beryllium will always be beryllium 2 when it becomes a cation. Sodium is always sodium with a 1 plus charge. Magnesium will always be magnesium with a 2 plus charge. They will not be you will not encounter magnesium 1 plus. You will not encounter aluminium 2 plus. You will always encounter aluminium 3 plus because it's in the third periodic tables. Same with potassium and calcium. These are all main group elements or representative elements where the charges of the metals coincide with the group that they appear in. Calcium is always 2. Potassium is always 1. But when you come to transition metals, you do not see only one transition metal, one charge for one transition metals. You're going to have variable oxidation states. Yeah. One of the biggest differences between transition metals with representative metals is that transition metals are able to exhibit variable transition states, variable oxidation states in their compound. The possible oxidation states from scandium to copper is shown in this figure down here. And note that the common oxidation state for each element will include +2 and +3 or both. The +3 oxidation states are more stable at the beginning of the series, whereas towards the end of the series, the +2 oxidation states are more stable. So if you look at this here, let me make that a little bit bigger. Yep. The red in this diagram this diagram here, the red in this diagram here, or the green in this diagram here, these are the most stable oxidation numbers for that metal. So for scandium, the most stable oxidation number is 3. For titanium, 4 is the most stable, but you get titanium 3 and titanium 2, but these two are not stable. Vanadium has +5 as the most stable oxidation number, but you do have 4, 3, and 2 for vanadium, but they are quite unstable. Chromium, you have 6 and 3 as the most stable. Manganese, you have 7, 4, and 2 as the most stable. And the ones written in black are unstable, even though they can exist. And these transition metal oxidation states can be matched with how many d electrons do they contain. For example, manganese 7 has D0 because all of these, manganese, all of these are lost to make manganese 7. 1, 2, 3, 4, 5, 6, and 7. All of these electrons will be lost when manganese 7 is created. So another thing that you must remember is when a transition metal gets oxidized, they will lose the s electrons first. The s will go away first and then followed by the d. For example, so if you have titanium 2, it will be 3d2. because 4s2 will be gone. If you have vanadium 3, it will be this 2 and this 1 will be removed, and you're going to be left with 3d2 only. Chromium, for example, chromium 3 is the most common. You're going to lose one of these and two of them. Yep. So you have 3d3 if you have chromium 3. So the s electrons are lost first when oxidation is happening. Yeah. Electrons are removed first from the 4s orbitals and then from the 3d orbitals when the transition metals become cations. Okay. You have the highest transition metal that you can see here. The stable is 7 and the lowest is 1. You have 1. Copper 1 is quite stable also. Yeah. And these are the number of d electrons that is corresponding to these oxidation states. So that is the first property of transition metal that is very different from other elements in the periodic table. One, they are able to have different oxidation states, unlike representative elements. Number two, the second property of transition metal complexes are they have colors. You have beautiful, vibrant colors for transition metal compounds. Yeah, because most main group ionic compounds are colorless. They look white. Because why do they look white? Because metal ion has a filled outer level, i.e. there is a noble gas electron configuration. So when, for example, sodium makes sodium 1, the 1 valence electron will be lost and you're going to be left with a neon, which is the noble gas, and it has all the electrons in the inner orbital or in the inner sphere, so there's not much. All these colors come from electrons jumping from one energy level to another. So if there is no jumping happening, no electrons jumping, then you don't get colors detected in our eyes, yeah, because when the electrons transition or move from one level to another, and when they come back down, they will release some energy, and the energy will match with a color. Yeah. If there is no jumping, then there is no energy released and there is no color. But for transition metals, electrons are located in partially filled d orbitals. They can absorb visible wavelength and making them move to slightly higher energy level. Yeah. So when electrons move to, because the d electrons, the d orbitals, you're going to be meeting this later in much detail, but the very, very small energy level difference in d orbitals make it possible for the d electrons to jump from one to another, and this jumping will produce energy being released or absorbed, and that energy is represented as colors of a certain wavelength to our eyes. That is why many transition metals have colors, striking colors. Okay, so if you want to see colors, this is the spectrum of electromagnetic wave. We start from the radio frequency, microwave frequency, infrared, visible light, ultraviolet, X-ray, and gamma ray. So when we move from low frequency, which is long wavelength, yeah, this is long wavelength, but low frequency, the energy is low because energy is, this is the Planck's equation, yeah? You don't have this in your notes, so you can write it down yourself. I have enhanced this particular paragraph with this picture. So energy is equal to H nu. Nu is frequency, and nu is C over lambda. So at the radio frequency, for example, the wave has low energy, it has long wavelength. But in the X-ray, the gamma ray, those electromagnetic waves are high energy waves. That's why when you are going to an X-ray department in the hospital, all the um, staff will be going out of the room. You will be left alone in the X-ray room because they don't want to be exposed to the X-ray, to the Sinar X, to the X-ray, because X-ray is high in energy. It has short wavelength, so it can interact with our cells. So avoid unnecessary exposure to X-ray because those are high energy um, radiations. Visible light occurs somewhere in the middle, around here, between the wavelength of 400 nanometers to 700 nanometers, and the electrons jumping, or when I say jumping, they are transiting between one d orbital to another d orbital. The electrons jumping between the split d orbitals experience the right amount of energy difference to produce electromagnetic waves with lambda between 400 to 700 nanometers, which is here. Hence, you get to see colorful transition metal compounds. Yeah, that is why the color exists. So the first criterion of a transition metal compound is the metal has variable oxidation state. Number two, the metal has colors. The metal cations has colors. They have colors because of the uh, uh, movement of electrons within the split d orbitals. Okay, we will go through that much later. Now, the exception to the colors are scandium, titanium, and zinc. These are all colorless. Scandium, titanium-4, and zinc, they are all colorless. Because, why are they colorless? Because the metal ions have either empty d orbitals. In the case of scandium-3, here is scandium-3, sorry, scandium-3. And titanium-4, you have 3d0. This should be superscript. Okay, you have 3d0, so there are no electrons here to jump around, so there's no reason for colors to appear. Or either they are empty or they are full. Full is in the case of zinc, because zinc will have 3d10. If you can recall, zinc is like this. Oopsie. Yeah, zinc. When zinc has lost 2 of these electrons, it's going to be left with 3d10. When all of these orbitals are full with electrons, then no electrons can move because it is full already, no room for movement. So that is why zinc compounds are always white. Yeah. So you have scandium oxide is white. Titanium is also white, and so on. All this is copper sulfate, and so on. This green is nickel nitrate. The red, the violet here is cobalt chloride, and so on. They are all nicely colored. So two properties of transition metal complexes. One, they have variable oxidation numbers. Number two, they have colors. And number three, the third difference between transition metals with representative metals is transition metals display magnetism. Yeah, magnetism. They have paramagnetic properties. Yeah. Now, magnetic properties are related to sublevel occupancy. Yeah. You will learn this much deeper as we go along in our coordination chemistry. Recall that paramagnetic substance have unpaired electrons. Do you still remember my explanation about oxygen? Oxygen is paramagnetic. It has unpaired electrons. So paramagnetic compounds have unpaired electrons. Now, paramagnetic compounds are attracted to an external magnetic field. When you apply magnetic field to a paramagnetic compound, you will notice that that compound is going to be attracted to go into that magnetic field. Yeah? Whereas diamagnetic field, which is substance that do not have unpaired electrons, substance that have only paired electrons, called diamagnetic, they are unaffected or slightly repelled by a magnetic field. So when you have a magnetic field going on, you put your diamagnetic substance, it will be repelled, pushed outside of the magnetic field, whereas the paramagnetic compounds will be pulled into the magnetic field. This is the two opposite properties of paramagnetic compounds and diamagnetic compounds. And this paramagnetism is shown by transition metal compounds. You do not see much other metals, non-transition metals, displaying paramagnetism, only transition metals. Yeah. Most main group metal ions are diamagnetic, for the same reason that they are colorless, because all electrons are paired up. Yeah. Transition metal ions with D0 or D10 configurations are also colorless and diamagnetic. In contrast, many transition metal compounds are paramagnetic because they possess unpaired D electrons. For example, manganese sulfate is paramagnetic. Manganese is a transition metal. Manganese sulfate has unpaired electrons. Manganese sulfate is paramagnetic. But calcium sulfate, calcium is not a transition metal. Calcium is a representative metal. So calcium sulfate is diamagnetic. It is not attracted to magnetic field. Yeah. The calcium ion has the electron configuration of argon, whereas manganese has a D5 configuration. We will deal with this magnetism, we will deal with colors as we go later into crystal field theory. But this is just a sneak preview of what we will encounter. So I think I'm going to stop here for this lecture. My next lecture, which I'm going to record very soon, is on coordination chemistry. So that's it for now. I'll see you in my next lecture for coordination chemistry. What I have covered in this particular lecture, lecture 9, are on the properties and the electronic configuration of transition metals, the properties of transition metals, and how they are different from main group representative metals. So, okay, that's it now. I'll see you in the next lecture. Assalamualaikum.